Okay, before our long break, we started Chapter 6, and I'm going to transpose that information from that blackboard that I have printed out t- to this OneNote page for our notes. And we'll start with Chapter 6.2, and it deals with perimeters. And perimeters essentially is just the distance around a polygon. Let's change the thickness of this a little. So for example, we have this distance, which is 3 BC, BA, AB, BC, 3 and 3, 3 plus 3, CD has a distance of 5, DE has a distance of 2, and AE has a distance of 4. We add all those up, we get 17. So that's essentially how we're going to do perimeters. We're going to handle perimeters. So when we have a situation down here, we can look at some common perimeters, like for example, the perimeter around an equilateral triangle. Again, this is all review. We have all the sides have the same length, W. So the perimeter equals W plus W plus W, or 3W. And a square, all the sides on a square have the same length, so the perimeter is W plus W plus W equals 4W. The perimeter of a rectangle is W plus W. We have a width, and then we have a different length, plus L plus L. So 2W plus 2L, or we can pull out the 2, and we have 2 times W plus L. Finally, we talked about the perimeter of a circle, and we've done this a number of times, where we see that if we take the radius of any circle, that we could lay that radius like for example, pretend like you have a piece of string that is the size of the radius, and you lay it along the outside of the circle. You're going to get 6 of these radiuses lengths that go around the circle, and you'll still have a little bit left, and that'll be like 0.28 r. And we see that somewhere around 6.28 times r is the same thing as 2 times 3.14 times r, and 3.14 we recognize as that famous irrational number pi. So 2 pi r is the perimeter of a circle. Okay, and that was it for section 6.2. Very short section. So we jump on to 6.3, where we start to talk about areas. And back here in 6.2, we kind of jumped ahead a little, and we discussed areas of some simple polygons. Like a square, the area was length times width, but since these are the same, it's W times W, or W squared. The area of a rectangle, again, length times width, so W times L. So those are 2 simple areas that we did there. So we're going to do a little more complicated areas here in chapter 6.3. First one was the polygon, and the area of polygon just turned out to be the length of the base times a perpendicular distance from the base to the top, from the base bottom line to the top line. So this distance here is perpendicular, so right angle there. So that turns out to be the area of a parallelogram. And the way you can see that works is, you think if you take this little triangle here, where I have this dotted line, and you chop it off, you could move it over here, and you'll see that it makes a perfect rectangle. And we already know that the area of a rectangle is base times height. So here's an example of it. Suppose you have a base length of 5 inches, which means the top length has to be 5 inches if this is going to be a parallelogram, and these sides are going to be parallel. These lengths have to be the same. So then we have to be given or we somehow have to figure out the height here, the perpendicular distance between these two lines, the bottom and the top. And that distance I have written here is 2 inches. So the area of this parallelogram is 2 times 5. Notice I did not indicate what the length of these sides were, because we didn't need it to solve the problem. Okay, triangle, you can do a similar thing. We have a perpendicular distance here, a line that's perpendicular here. This is actually what we'd call the height of our triangle. So we can flip this triangle around. You'll see that you have a rectangle. So the area of a rectangle is width times height, or b times h. But since we're only dealing with half of this, then it's 1/2 b times h. So that works on any triangle. And what we have to do is we have to figure out what this height is. It's perpendicular distance to this height of our triangle. We have to figure out what that is. And once we figure that out, we can see that, oh, we can just create a parallelogram. And we already know that the area of a parallelogram is 1/2 base times height. So any triangle that will work for. Moving on to a trapezoid. So we did some of this in class where we tried to figure these things out ourselves. But with a trapezoid, the area, the formula we're going to use is we're going to have a bottom base, and then this top length is going to be the small, we'll say small b. So big B, small b, and then we'll have a height, and that height is as a perpendicular line, so it represents the distance between big B and little b. So we found out that if we take big B and add it to little b and divide by 2, then multiply that by height, that gives us the area of our trapezoid. And there's a couple ways we did to figure it out. I think it was Jennifer in class recognized that we could split this up into a triangle, 3 triangles, and then you could just solve the problem 3 times and you get the same relationship here. Or you can cut this into 2 triangles the way I did down here, and both of these triangles have the same height. You can see this line on top here is horizontal and parallel to the line on the bottom. So this distance, this height distance, is the same for both of these triangles, even though the triangles are separate. And you would have for the base of this top triangle, the little b, and the base of the bottom triangle, you can make the big B. And that's just one way to do this. And so then this is the height of both triangles. So you could just split this up into the area of 2 triangles, which I did here. 1/2 base times height, 1/2 big B times h. So that was how we came to solve for that. So finally, we wanted to talk about the area of a circle and how we could visualize this. And we start with a circle with a radius r. Radius is half the diameter. And I cut that in half, and I section it like a tangerine, and I cut it in half. Then I spread out the pieces like you're opening up an orange or a tangerine, so that this half circumference, now I lie it flat here, and we have our sections of our tangerine like teeth pointing upwards. I do the same with this one. I pull it out, and both of these have a length. If the overall circumference of a circle is 2 pi r, then half of it is pi r on the top and pi r on the bottom. And then I just said, let's just kind of put our hand against this and push it up, and you can see that we make kind of like a rectangle out of it. So the area is r times pi r, which is the same thing as pi r squared. So that's the area of a circle, and that's kind of a way to do this. Another way to think about this, if you don't want to, if you think that that's kind of hokey and cheating a little bit to mash this up into a rectangle like I did, what you could do is you could section this off into tinier and tinier and tinier pieces here. And if you do this like close to an infinite number of times, when you open it up, it's going to look almost like a rectangle. This edge is going to be almost straight up and down. And this edge is going to be almost straight up and down if you have a whole bunch of wedges. And so that approaches a rectangle as we slice it up an infinite number of times. So that's another way you could look at it. So the next thing we're going to do is we're going to move into chapter section 6.4, and I'm going to do that in the next video.